All right, Denny's ready, so we are good to go. So, you ready? You ready? Okay, speak directly to the clown's head. Class. Thank you. It's not a mic, just so you know. So I pretend like it is. So, kind of like, you guys ever watch The Price is Right? No? Where like go and yell at stuff. $1. Anyway, he's got like this little bitty mic that he puts up and beep. Anyway, all right. So we're gonna do uninhibited growth and decay. This is a lot of not calculus. This is algebra, but it's all based on a calculus formula. So, solve differential equations involving uninhibited growth and decay. Uninhibited. What does the word uninhibited mean?
Yeah, that says a lot. I'm trying to remember what inhibited.
Okay, now, do you want to get real scientific with it? It's not retarded. The word retard means to hold something back, to keep it. And so, like a fire retardant, it is. Inhibit means to keep from, so hold it back. Being held back for any reason at all. So, uninhibited is,
Moving forward.
okay,
Unrestrained.
unrestrained. That's an even better one right there. So, is that what you were going to say? Yeah, you just didn't say anything. You were thinking it, Bill. I saw it. It was right there. Okay, unrestrained. So that means that it can go forever. Kind of like, my favorite type of problem to go along with is zombie apocalypse. Is there an uninhibited or an inhibited growth at a zombie outbreak?
Uninhibited growth, yeah.
Uninhibited?
If you're in China.
Wow, okay. So why China?
That's where all the movies come from.
Oh, that's where all the movies come from?
Well, Train to Busan, Museum. Or was that not in China?
I don't know. I didn't know that Chinese were involved in, corruption of all American cinema. Oh wait, yes I did. Anyway, but hate to break it to you, uninhibited. What would it be if I told you that it is inhibited? What would inhibit that?
Death. You slowly decay.
Kinda. If we were going to have a zombie outbreak, is there some maximum amount of zombies we could actually have?
Yeah.
What is it? The entire population, right?
Unless you slowly.
And we just get to that point right here. That would inhibit it. So, if it's a zombie outbreak, okay, do you think zombies are reproducing? No, this is not that. What's that Warm Bodies movie? I actually like that.
I thought of radiation.
Radiation?
Just mutate the zombies so they reproduce somehow. Get that small percentage.
I was actually just thinking about the movie Warm Bodies, where the zombie, his heart started beating again, and fell in love with this girl, and blah blah blah.
I thought of that video game. The zombie video game.
Okay, anyway, zombies don't reproduce. Okay, so that would be one to go along with this. So growth and decay. So we have a formula we're going to use right here. This is, we have, okay, it is the derivative, okay, so what we have from here, it is of A divided by D of T. So it's actually taking it in terms of time, getting it in terms of time. So if K is greater than 0, then there is a growth model. If K is less than 0, that would be negative numbers, right? That would be a decay model. Okay, suppose the initial amount, A sub naught, this is the initial amount all the time, okay, of a subject is known, giving us the boundary condition or initial condition, A sub naught when T equals 0. See these two things right here? This is key to answering everything. A sub naught, T equals 0. So that means your starting amount when T equals 0. That's your starting time. Okay, always starting time is going to start at 0. You don't start at negative. Okay, that's weird. Okay, you don't have negative time. This is not NASA where they go T minus 14. Okay, and then, so, right there. So we solve differential equations. Right here we have dA over dt is equal to K of A, which is, now, what does the capital letters always mean when we're actually doing these? Not the integration. Okay, the capital letters refer to the integration of this. So if we have the derivative of the integration of this, because we're always going to be given a rate, some type of rate out of this, and we're actually getting the population, which is the area under the curve, based on a rate, and that's what we have right here. So we have a growth, a population, a total area under the curve, given a rate that we have here. Okay, so if we differentiate the equation from here, both sides writing as this, as, okay, we have dA over A is equal to K of dt. Then we integrate both sides of the equation on the left with respect to A and on the right respect to T. So that's how all this works out. And I just said a whole bunch of words and confused everyone all at once. So, see these two things right here? That's all you care about. Okay? Is that easy? Okay. Here is the integration for all this. I'm giving it to you. I'm telling you what it is. So we're integration of all this, working down, boom, 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 initial condition, blah, 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 blah. We get a formula. This is my formula. So, in basic terminology, okay, my population, capital A, is equal to my initial amount of the population, e to the kt. Does that make sense? Yes? That's what we're going to get there, okay? Here's the functions for my growth and decay for both of these, with examples of my growth, which is going up right here, where k is going to be greater than 0. K is less than 0. I have a decay with my initial starting amount. And if you notice, okay, my decay, it looks like it is going to go as a what? What are those things called? Okay, it's going this way forever. What does it look like it has right here?
Closer to 0.
Yes. There's a word to go along with it, though. And it sounds like a bad word.
Asymptote.
There we go. All right, asymptote. So, looks like it's going to be an asymptote. So it's going to be approaching 0 for a very long time here in my decay. Assume that a colony of bacteria grows at a rate proportional, that's important. The word proportional is important here. To the number of bacteria present. The number of bacteria doubles in 5 hours. Okay, that's important. Okay, doubles in 5 hours. So I know that my amount, so let's go ahead and take my A equals A sub naught E K T. That's the formula I'm using. And it says it doubles when? In 5 hours, right? If it doubles in 5 hours, let's go ahead and use that information. So, in 5 hours, so when T is what? 5. So, it's going to be A sub naught, so my initial amount, E K of 5 is equal to, what do you think I should write over here for this side?
The amount of bacteria total?
Okay, yeah, but in time, what was my time? 5 hours, right? So what did it do in 5 hours?
Doubles.
It doubled, right? Do I know what the amount is?
No.
No, I just know what my original amount is supposed to be, and it's doubled. So how would I show that? Not 2x, but you got it right. You got it right here. We're not using x's though, but what are we using for my amount?
2A.
A. Which A? A sub naught. A sub naught means my initial amount. So you you had it right there. So my initial amount, so A sub naught is what my population is at the beginning. That's what that is. That's important. Okay, so we know that it's going to double my initial amount. Let's do a little bit of algebra. What can I do to both sides here?
Divide by A over E.
Yeah. A sub naught.
Oh,
A sub naught, or you refer to it as my initial amount. Okay?
initial.
So there we go. So divide both sides, and I'm left with 2 is equal to E of 5K, right? Like that. How do I undo an E? Because I'm trying to get that K by itself. That K is my variable. Natural log, right? So I'm going to ln both sides. ln both sides. But if I ln E, what happens there? I just get?
One.
No.
No.
It is 1, but in this problem right here, it would be 5K. So if I ln that cancels the E, so it's going to be 5K is equal to ln 2. Because I'm ln'ing both sides. I want to get what by itself? K, which is going to tell me my rate. That's the rate I'm trying to find. So divide by 5. There we go. So now I know what my K is going to be. So it is going to be proportional to my next one. If the number of bacteria doubles in 5 hours, okay, that's important. That's what I use to get my initial rate of K. So is this a positive number? Yes. If it's a positive number, that means, is it a growth or is it a decay? It's a growth because it's going to be K is positive here. How long will it take for the number of bacteria to triple? Okay, so we're looking for it to triple now. So again, we have A equals A sub naught E K T. And now, since I know ln of 2 over 5 is equal to K. Did I write that correctly? Yes. So, given this much information, I want it to triple. How would I state that it's going to be tripling? Let's go back to the question again. Okay. How long? So what am I looking for? Time. Very good. I'm looking for time. So how long will it take for bacteria to triple? Okay, so that means I'm looking for T. I'm going to be looking for a T. And for it to triple, I would write what?
3 initial amount?
Yeah, 3 times my initial amount. There we go. So 3 times my initial amount. So it's going to be 3 A sub naught is equal to A sub naught E. My K value's up there. I'm just going to put this right here and just plug it in later to make the math look a little bit easier. So now I could solve for the T. That's what I'm looking for here. How long? So divide both sides by A sub naught, or my initial amount. 3 is equal to E K T. And now again, I'm going to ln both sides. So I'm going to get ln of 3 is equal to KT. And I know what K is, but instead of plugging that in right now, can I just divide both sides by K?
Yes.
Yeah. So it's going to be ln 3 over K is equal to T. So I'm dividing by K, but I got a fraction though, right? I don't like dividing by a fraction. What do I do instead? Multiply by the reciprocal. There we go. Multiply by the reciprocal. So the reciprocal of that is going to be 5 ln 3 over ln 2 is equal to T.
Do you have a tissue anywhere?
Here, I got some butt wipe.
Yeah.
All right. Did you guys plug in the calculator, or everyone just still waiting for me to do it? I guess everyone's just still waiting on me.
At first I thought you were able to cancel out ln until then I realized the different values.
You can kind of use some rules on it, but it's not going to be helpful. And it would just be erasing things, which is not mathematically sound. All right, what do we get for a t? T is going to be about, and round it to 3 if I could, please. 7.9245. So if I'm rounding it to 3, 7.925. And t in this case is what? Did it actually give me time? Is it years, months, decades?
Hours?
Hours. There we go. Does that make sense now?
Yeah.
Happy day?
Yeah, that's just a recalc.
Okay, yeah. But it's all based on the calculus formula, and you don't have to do the calculus. You just have to know what to plug it into. So, for radioactive substance, the rate of decay is proportional to the amount of substance present at the given time t. If A is equal to A of t represents the amount of radioactive substance at time t, then same thing, where K is going to be less than 0 depends on the radioactive substance, referred to as the half-life. So the whole definition of half-life, carbon-14 decays to become carbon-12 in a very, very it hits this equation perfectly. It really does. Okay? So half-life means, since it does decay at a rate like this exponential rate, but it is a decay rate, for this one right here, the half-life means that's when I will have 50% of it left. There, if I start off with 100 and I plug it into the half-life formula, I'm trying to find out when it's going to be down to 50. That's the whole point of this. Skull of an animal found in archaeological dig contains about 20% of the original amount of carbon-14. That's important. So that's going to be this formula. I'm going to try and solve for this. Okay? I'm going to try and solve for that. Now I need initial conditions to actually set up my formula. If the half-life of carbon-14 is 5,730 years, okay, that's giving me the half-life formula already. So this is where I need to set up everything that I have. Does that make sense or no? How long ago did the animal die? So let's write out my formula. So A sub naught is equal to, I'm sorry, not A sub naught, A equal to A sub naught E K T. All right, if this is the half-life formula, my initial amount is going to be here. What's going to be over here on the left-hand side? Yeah, 1/2 what? Initial amount, very good. So it's going to be 1/2 the initial amount. So 1/2 my A sub naught is equal to my A sub naught e to the k, and I know my t because I need to find out my initial rate. This is going to be my rate for this, 5730. And just so you know, carbon 14 is not the only thing that they do with this. So if you plan on going into medical, they use radiation treatment in cancer for a lot of cancers. And do you think they actually do gamma rays and turn people into the Hulk? No. Okay? They use certain types of radiation. There is some very, very rare radioactive isotopes that they use that has a half-life of 7 days. That's important. Okay? So with those things, those are still radiating the body, but that's how they use. They don't actually just hit everyone with nuclear waste. What do I do to both sides here?
Divide by initial value.
Yep, divide by initial. Okay, so I get 1/2 E K 5730. Oh, there's an equal sign there. ln, right? ln both sides. They're going to have a couple ln rules though. ln 1/2 is equal to
K.
yeah, k times 5730. And one of those ln rules, that 1/2 on the inside. What can I do if there's a 1/2 on the inside?
Oh, natural. No, I thought absolute value.
No, there's a natural log. Can I break up that fraction?
Oh yeah, you can.
And it turns into ln of
1 minus
ln of
2.
very good. But do you know what the ln of 1 is? 0. ln 1 is 0. So it's going to turn into this. So it's ln of 1 minus ln of 2 is equal to my k 5730. And this right here is 0. So when I have that 1/2, could I just rewrite it? If I do this right here, it's just a negative ln 2 times that, right?
Yeah.
Okay, because ln 1 is 0, so I could get rid of that part. So whenever you see fractions like that inside an ln or a log, you could break it up into two separate, and because ln 1 is 0, that cleans up a lot of my problem. That cleans up a lot of it. And now let's do a little bit of math. So we solve for k here. So I'm going to say that k is equal to negative ln 2 over 5730. Alrighty. So now that we have all that set up and all that ready to go, now let's address my actual problem. So what can I do? How would I write my actual problem here? Without zoning out. How do I write the actual problem?
2 over 10.
2?
10.
Yeah, you can write it as 2 over 10, right? 2 over 10 what?
The initial value.
2 over 10, initial value. Initial value, A sub naught, is equal to?
A sub naught, E, and then K value is kind of there.
Yeah, I'm going to leave K in that form right there.
Yeah.
Just, I'm going to plug it in at the last, and we're trying to solve for T. So yeah, the 2 over 10 that works out. Or I could have just said 1 over 5, right? Or could I just put 0.2?
Yeah.
Yeah, I could do any of those.
Still the same.
Yeah, it's still the same. Do I need to know what the actual initial value is here? Say no.
No.
What's going to happen to both sides?
Just divide by the initial value.
Divide by initial value, so either way, that's going to go away. So, I'm going to end up with, I'm going to reduce 2 over 10 to 1 over 5 to make my math a little bit easier, equals E, K, T, ln 1 over 5, K, T. And that ln 1 over 5, that one's actually pretty good. I did that for a reason. So ln 1 is 0, right? So I could write this as negative ln 5 over k is equal to my t. And now let's plug it in. But I don't like fractions over fractions. I really don't. So I instead like putting it multiplied by the reciprocal. So after I plug it in, I'm going to multiply by the reciprocal instead of dividing by k. I'm going to say that negative negative is going to make that one a positive. So 5, 7, 3, 0, ln 5 over ln 2. Why? You know what? This is a horrible color. Why'd you let me choose this color?
You felt like a Barbie.
I know, right? There you go. Now it's even worse because it makes it look like it's three-dimensional. It's popping out. There's a shadow on there. All right. Now calculate that for me. How long is that going to be?
Is that both positive or?
Yep, because this one over here was negative, and this one over here is also negative.
I thought by doing the reciprocal you change the sign.
No, 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 no.
Okay.
That was perpendicular. Opposite reciprocal is when you have the perpendicular slope.
Oh, okay, okay.
Right. If the slope is 1/2, perpendicular to that is a negative 2.
Just the tangent thing.
Yeah.
13,304.648.
13,003 what?
304.648.
Is that a long time ago?
Not really. Yeah.
13,000 years ago.
Not as long as dinosaurs, but yeah, an extinct animal. Like a
Yeah,
dinosaur.
it's not dinosaur time, right?
Yeah.
No, that's still in the era. I think that's the age of Ramses the Great. About 13,000 years ago. It is Egyptian time frame where, you know, they.
The late glacial maximum.
Oh, okay. So this is like a mammoth.
Yeah. A comet struck the younger Dryas event.
Oh yeah, no, that's even longer. That's
Yeah.
yeah, the younger Dryas. That's where Atlantis actually disappeared from. It was aliens. All right. Questions, concerns, complaints. I'm going to leave off there before we actually get into the more complicated ones, where we are going to have a constraint. We're going to inhibit our growth now. But that's going to be tomorrow. So make sure you like, share, and subscribe. Hit that notification and support my channel.